Our next speaker is Eduard Royal from Sorbonne University, Paris. So he'll introduce the talk that he's going to give, and I'll leave the stage for Edouard.
So thank you for the introduction and the opportunity to do this talk. I'm going to try to get full screen now.
Control L.
Control L. Thank you. So yeah, so today I'm going to discuss some work I did with Eugene Bielowski with Atmila and Michael Eichenberg with the Propagation Institute. And so the idea is to give some method to train a CNN on multiple machines. So just to give some context, because I got the impression there are many people from different backgrounds, like NLP, audio, or vision. And so the kind of benchmark I'm interested in corresponds to vision on ImageNet. So as you might have heard, there are some neural networks so that AlexNet, VGGs that have some superhuman performances. In general, the accuracy is measured in terms of top 5, which means that the prediction of your neural network should be in the 5 first predictions that your neural network has done. And what's actually interesting on this slide is ImageNet. So ImageNet is a very large data set, which is about 200 gigabytes if you have it on your hard drive. You're going to have a million images. Those images are quite large, which means that there are several kilobytes, but actually when you're going to process them, you're going to use a batch of images. Which means that if you want to handle this kind of data set, you really need to have a specific hardware. So I know that now it's getting more common to have the corresponding hardware to run those kind of algorithm, and that almost everybody with say $3,000 can get the corresponding hardware to obtain those performance on ImageNet. And during this talk, beyond the training, the metrics that I want to optimize is actually the accuracy of my model. So what I want to develop is, to introduce you to, is some algorithms that allows to train a neural network on multiple machines with model parallelism, with a limited drop in accuracy. So very precisely, so I want to. I'm questioning the fact to train a neural network on multiple machines in an heterogeneous environment where you might have some poor connectivity between the different machines. And so the solution we propose is an algorithm that allows to put a given layer on a specific machine and to train them in an asynchronous, potentially asynchronous manner, and particularly decoupled. So, in other words, the dream, so here what you see here is a schematic way to have a ResNet. The dream would be to split your neural network in multiple layers and to put a given block of layers on a specific node and to train them as good as you can. So, just to give some background on training CNN. There is a schematic way, so I guess everybody knows, some of you know the AlexNet that you can see here. And so a CNN typically takes an input signal and propagates it through different modules. Those modules, so here are called Phi, and those modules have some parameters theta j. So in general, you're going to have, for example, a convolutional layer that's going to be combined with a row loop. And that's a nonlinear operator. So once you have fixed your empirical risk that you want to optimize, and in general it's going to be a classification risk, you're going to train with some LGD algorithm your neural network, because you have the assumption that every module is differentiable. You're going to use some techniques like mini-batch LGD. And in general, this optimization is non-convex, which means that it can be very complex to analyze. And also it requires a lot of recipes. So that's something which means that when you have a standard procedure for training a neural network, it's very difficult to apply some minor modifications without leading to some major drop of accuracy. And in the context of distributed training, this is the idea that you have an algorithm that you want to run on, say, K machines. And what you would like is to get a speed up, which is going to be linear in the number of machines. So of course, this is a bit optimistic because very often you have some issues such as connectivity between your machines. Some machine might die, some machine might actually drop during the training of your neural network. And there are two settings which are very often used. So the first one, I think this is the most common, the centralized setting, where you have a master node which is connected to some slave nodes. And so the idea is that each of those other nodes can just communicate with the master. And in general, the master is the one that is going to aggregate the result of the other nodes. Another setting which is of high interest to me, but I will just mention it briefly at the end of this talk, it's a decentralized setting where there is no specific master node that is supposed to guide the training of the training procedure of the model. And where here you can have some very different topology that models the way that the different nodes are connected. And in general, for distributed settings, when you want to train your neural network, you're given some loss functions. So here it's going to be f of x theta. Here x are going to be my samples, where theta are going to be my parameters. And so one can really distinguish two settings, and there's the assumption that your loss is separable, which means that you can write it at this very nice sum here. There's one which is a data parallelism, which is pretty much used when you're going to do some mini-batch SGD, because in this case, not only you're going to split the entire training set into mini-batch, but also each mini-batch itself can be processed independently, for example, on different curves, as I did here on this figure. And then there is one which is, it's slightly more difficult to characterize it fully. It's a model parallelism. So it's the idea, for example, that you could do here some coordinate splitting, which means that here your model will be both separable in either your samples, either your parameters. And if you have enough machines, you see on these figures on the right that you could distribute each of the computation, for example, of the gradient on your loss on each of those machines that you could potentially have. And so in this talk, I will be mainly interested in model parallelism. And now I really need to give you some intuition about backpropagation training. So here, what you see here is the way you're going to apply the chain rule to compute the gradient of your neural network. So it means that each of the delta theta j does correspond to the increment, so the gradient step that you're going to apply to your model. And so what's happening is that you're going to forward your input x, right? So that's that does correspond to the black arrow, and once your input has been propagated through the network, you're getting to the loss. And then you're going to get the retropropagation part, the backpropagation part, which means that on the red flag, you're going to compute each of the intermediary gradients, and from that, you're going to estimate the corresponding increment of the gradient with respect to given parameters. So there are some formulae, but you can just think of it as this diagram. This is completely enough for this talk. And so there are tons of issues with backpropagation. So one of the first one is that memory-wise, you need to store each of the intermediary features if you want to compute the intermediate gradients. This can be quite high-dimensional because, you're going to work by batch, and so it means that each of the batch sample must be stored on every layer. Secondly, you need to synchronize each of the layers, which means that at every step of the optimization, all of the layers have to be coupled, which means that the dots correspond to the same, they have to be at the same step of the optimization with exactly the same samples fed with the same samples. There is a third thing, which is the bandwidth, which means that you must have a high connectivity between each of your layers, otherwise you're going to have a huge slowdown when they're going to be propagated through your network. And finally, you need to find some method to compute efficiently the gradients. So backpropagation is great because it's working in practice, but one says that if suddenly one would like to distribute the model, all of those four aspects makes it quite challenging. And in fact, from the hardware point of view, because here, like, everything I said just some like sort of principle, but like actually, to be very precise, if you have, when you're training a CNN, in general you have a single machine, or it can be a cluster too, but like, this machine will have a huge amount of memory, and typically will be pretty homogeneous, which means that you have almost the same cluster, but the same type of GPU on your machine that's going to be connected, for example, with NVLink link, which means that you have a high connectivity between each of the GPU. That's going to be centralized too, which means that you have a machine, a master, that's going to have a huge amount of cores, that's going to synchronize everything. That's great because you might have 1 terabyte of memory on your machine, 1 terabyte also of GPU memory on your machine. So this is the ideal setting, but I'm pretty sure that not everybody here possesses this kind of hardware. And what, on the contrary, we have, in general, it's more like a collection of machines. That can be some bad computers or good computers with some heterogeneous hardware that could be potentially well connected, poorly connected. Also, you know, I mean, some machines might be isolated from the others on your network, like there are many challenges, and that's the setting that does interest me here. So ideally, I would like to have a cascade of machines that are just going to be directly connected one another to the other. And you can think of it as if you wanted to put a single layer on a given machine. And that's all done in this, I mean, like the connectivity is similar to the feed-forward connectivity of a standard neural network. And that's more common. That's the kind of thing that in general, in practice, you might have. Also, you should know that I did not include any feedback between the last machine and the first machine. So that's our setting. I mean, going from something which is pretty standard, where you're going to have some multi-GPU, to a non-ideal setting when you want to train your neural network purely with the propagation. And trust me, if you just try to do it with 4 machines in this way, you're going to have a super huge slowdown. So for example, if you code with PyTorch, if you ever run like the main script to train a neural network via PyTorch and ImageNet, you know that you need to use SSD rather than HDD and these kind of things because you have this data parameter which is completely slowed down in those with those settings. And so to try to train the neural network on those in this environment, I need to introduce a notion that was introduced in DNI, so this is also a paper by DeepMind, which gives a notion of locks. And so in the work I'm going to present you, I'm going to try to remove those locks. So one of the first locks, so you have several modules. They're connected via forward. There is a backward which is implemented in it, and you have the update of the parameters, which just exactly correspond to what I showed you with the propagation algorithm. So the first lock that we would like to remove is a backward lock. Is the fact you have to wait to fully forward your feature from the beginning of your neural network to the end, and to wait to backpropagate the representation before to update your rate. The second lock does correspond to the update lock. It's the fact that a given layer has to wait for the forward to have been fully completed before to update its own lock. And one which is slightly ill-defined, it corresponds to the forward lock. It's the idea that if you're at the end of your neural network, if you take the representation at the end of your neural network, that should correspond to a batch of samples that have been propagated at the input of your neural network. Which means that when you want to process your data, you need first to process them to the next layer. You need first to input those data in the layer before, etc., etc., etc. And so they came up with like a very interesting strategy. So it was a paper by mine. So instead to compute the gradients, they designed a neural network to estimate the gradient step that should be computed by a backward of a neural network. So that achieves completely that removes the update lock and the backward lock. However, one of the issues with that, when you're going to train this kind of neural network, it's pretty obvious that the gradient is super high dimensional. You have a lot of variability in your problem. So estimating a gradient, which is with your neural network, can be very challenging. And so the performance of this kind of architectures are quite below the end-to-end learning that you might have with a standard neural network. And so we introduced some strategies like to decouple the layers of a neural network. So I should mention that it's very similar with the local learning that you might heard about, like that was done by Nopland and Innes. And everything started with a super simple observation. So when you take the features of a neural network, if you look at them, so here there is a binary classification task. Progressively, they're going to be more linearly separated. So you can actually measure that, which means that if you apply your linear classifier, so here it's a SVM, on the subsequent representation of your neural network. So you take your feature at the third layer, at the fourth layer, at the fifth layer, you're going to notice that they progressively improve. So one question is, can we obtain the reverse? Which means that can we stack progressively some features which are progressively better? And actually the answer is yes. So it's a super easy, simple principle. So we can train a neural network layer per layer. So say that you're going to train the first layer, fine. You train it until convergence, you freeze your layer. You stack again a new layer, you train it until convergence, you freeze it. And you're going to iterate the strategy. So you need, of course, like an auxiliary classifier, like to get the good prediction of your, to get the good gradients at a given layer. And it's a very simple idea. I think that was one of the first ways to train neural network in 2000. And it does scale on ImageNet, so we got to work on that. And what's interesting here is that you do not need to have some gradients that are going to be propagated, that are going to be exchanged between the different layers. And so you can also get some very decent accuracy in ImageNet. So here's what you get with a very shallow neural network that you stack on top of your layers to train them in a sequential manner. And in fact, if you try this idea, but instead to train a layer per layer on neural network, let's try to do it in parallel. So how can we do that? So here you might start with an input signal here, and you're going to propagate it. At the same time, while you're going to propagate your signal, you can in parallel forward it in the loss of the first layer, but you can also propagate it in the loss, in the second layer. You can do that in parallel. That doesn't hurt, and actually you can compute the gradient, everything in parallel. And you can continue this kind of principle. You could stack more layers, you can train in parallel your layers, so you will get a substantial saving in memory, because then you just need to store, you do not need to store the features of the first layer. You can continue this process and just remove them during the training. And so you really have an algorithm which is decoupled. And the auxiliary classifier is something that you need to design so that it's going to be as small as possible and do not include any overhead. And you need to send the labels. And so if you apply this kind of strategy, so this is another schematic way to think about this training procedure. All the forward are synchronous, but like each of the backward can be done in parallel. So you really have this saving there. And the performance that you get, so of course you get a drop in accuracy, because here we have like put every individual layer on a different machine, but like the drop is minor compared to the memory savings that you can get. And with this, as you see, we unlock the backward and the update, because like you don't need to wait the full forward before updating a given layer. But in fact, you should do it by block. Which means that instead to split each layer on a different machine, just doing it by block, you're going to improve slightly the accuracy I showed you. So the bigger are your blocks, the better it is. And in fact, there is something a bit, to me that was a bit impressive. You can train the ResNet 152 with a minor, actually there is no drop in accuracy on a single machine thanks to this kind of technique. However, there is this issue with the synchrony and the bandwidth, because you need to communicate your features, and there's still a sort of coupling, because all the layers need to be synchronized. So how can we remove that? So what you can do is, for example, to add a small buffer that is going to store some features in some memory, And this buffer is going to feed a given layer and to sample those features, some batch of features from its memory. So in other words, you could imagine like you have two nodes. A given node has an internal buffer, and the first node is going to feed the buffer of the second node. That's great, because then you can be more asynchronous, which means that the second layer does not need to wait for the first layer to have completely accomplished its feature forwarding. You can wait. You don't need to wait. Like its internal buffer can be fed in any speed which is desired. But like this is completely asynchronous in this case. But like the main issue is that the forwarded features are huge, which means that you might have an issue to communicate the features that have been forwarded by the given layer to the next layer, because like you have a gigantic batch of features there. The second thing is that the buffer also will be large also, because the features are large. So if you store a buffer of size B, you need to you will store like B times the size of your features on each machine, which can be substantial. And so we end up with like a features compression solution. So you can imagine that you have a small dictionary, and you can try to quantify every intermediary sample so that they're going to be way smaller. And so when you quantify given features in a dictionary, you get a substantial saving, which is the logarithm of the size of the dictionary. And so in this case, that's great because the buffer is going to be substantially smaller. The features which are forwarded are substantially smaller, but the thing is that the features evolve dynamically, because like during the training of your neural network, they're going to evolve. And so it means that you need to synchronize the dictionary between two layers. And so we ended up with an idea that one can use some random dictionary and sample a new dictionary each time that we feel that there is a bias which is introduced in the process of optimizing our neural network. And this can be done with a limited amount of information communicated, because you can just share the same random seed between two machines and have the same dictionary with a limited communication cost. And so with this strategy, you can lock forward, backward, an update of your module. So it means that in some sense we have solved like the initial question. So we can do a completely decoupled asynchronous algorithm for training a neural network. So does it work? So for instance, I don't have an ImageNet experiment because it's very hard to make a simulator for these kind of things. But if you apply it on CIFAR 10, you recover the end-to-end accuracy. And this type of technique is pretty robust to, for example, slowing down the layer, which means that if a layer suddenly starts to lag, the accuracy will not be hurt much. And also to the buffer size of your given layer. Right. So I'm just going to finish very quickly, because with this kind of ideas, you can have way more principles that are also interesting. This type of idea, you can find them on frameworks like ByteTensor or HiveMind, for example. And the idea that you have some nodes that are connected together. You're going to input some data at some nodes, and they should together try to design a feature representation that's going to be useful for some tasks. But the thing is that the connectivity of the node, you might not know it in advance, and also it does not look like a neural network as before. And there are many questions which are raised that you could apply the kind of decoupled trade techniques that introduce to this kind of principle. So for example, how you can take benefit of communities, how to handle, for example, a malicious node that will be communicating between two given communities, how to handle how to benefit of the network connectivity, for example, if you have some cluster of nodes which are together, how to handle lags, how to guarantee the quality of a given feature. For example, you don't know if some of the features are good or not. You need to find a process to validate that. And some other type of ideas that you can get with this idea of decoupling is, for example, you know that some company is designing some good features, but you would like to use it in your framework. And actually, there are a couple of companies designing some good features. So first of all, how do you get the best features? It means that you need to have a sort of feedback between your node and the ones that are going to sell use those features. How to remain bit perfect. You don't want to share your test set that allows you to compute the good to estimate like the quality of your framework. Otherwise, of course, the company is going to to fool you. And how to assess the price of those features. So that's a lot of questions. Well, so in conclusion, I hope you convince that on some limited hardware with some decoupled optimization strategy, you can find some new paradigms that allow us to go further the end-to-end training. And I mean, this kind of technique like decoupled centralized application could be simplified. And so if you're interested in those topics, I got some job offers on my website. Thank you.
Thanks a lot. Are there any questions? Yeah.
Thank you for the interesting presentation. I was wondering how I can set this up. So are there any tools or libraries that already accomplish this, and hardware-wise, is there anything extra that I might need?
Right. So thanks for asking. So right now we got some source code. I think, so that's still some research projects, so the source code cannot be directly deployed. But actually, I mean, I'm looking for a research engineer and postdocs that would like to scale this kind of algorithm to changing benchmarks. Right now, we just use simulators because we don't have the infrastructure to train it on a large scale.
Okay, thank you.
Hello, thanks for the talk. I wondered how does this relate to graph learning, if it does relate in a way, because it is very like message passing with keeping the parts of differentiable graph in like different nodes. Has there been like any connection with this, or like is it being researched?
Okay, thank you for asking. So it's a great question. So like this work is more a proof of concept that it's possible to have a different topology to connect your nodes and to still get an okay-ish accuracy, to have a limited drop in accuracy. So actually that's some aspect I would like to study is what happens if the connectivity suddenly changes, what you're going to do, some knob drops. Are there some graphs which are better? Like for example, you can imagine some classification task where you estimate the quality of your network given some graph, and indeed like that's still doing some works which should be.
Do you see this paradigm merged with federated learning on some horizon or not?
Pardon? Can you?
Do you see this paradigm merge with federated learning on some horizon or not?
Okay, so, thank you for asking. So, so in federated learning, there's an idea that you want to be both private, with in general your algorithms are quite synchronous. But there is still the distributed aspect which is present. So I'm slightly interested by the privacy aspect. It's not the main focus on my research. But like, and there clearly some connection, but I think this is a work which is quite independent from federated learning. I mean, for now. And also, I mean, in federated learning, there is mostly this idea that you have like, say, 3, 4, 10 hospitals that are going to collaborate together. Here I got more in mind, like, you have like a bunch of users that have their computers which is idling, and that could collaborate together to build a gigantic model with all those resources which are currently available. Not like just 10 clusters of hospitals working together. So it's more the spirit of this work.
Okay, let's thank Edouard one more time.